Another consideration for SN2 reactions, other than the nucleophile and electrophile, those are the big ones for how they influence the rate of the reaction. But we also have kind of a third thing that can kind of come in and influence the reaction, and that is the solvent that we run the reaction in. So we don't always talk about solvent effects in these introductory courses, but it is very important for our substitution reactions because it can really affect the rate of those reactions depending on what type of solvent we have. So both of these solvent types, our polar protic and our polar aprotic solvents, they are both polar solvents, and we need polar solvents because we need to be able to develop or to stabilize those developing partial charges in the transition state. We also need to be able to solubilize our starting materials. So we usually will have that polar covalent bond. We're also going to need polar covalent bonds in our solvents in order to help solubilize those starting materials that we have. So they're always going to be polar, but whether they're protic or aprotic is going to matter. So polar protic solvents are going to have H's attached to electronegative atoms. What we learned about H's when they're attached to electronegative atoms is that they can actually participate in H bonding. So that's going to be a key thing that these polar protic solvents are going to be able to do. They're going to be able to H bond. We're going to see how that comes into play with our SN2 reaction. So our polar protic solvents are going to be things like water, methanol, ethanol. We have this OH bond here that can participate in hydrogen bonding. Acetic acid, we also have that OH bond. Ammonia, we have an NH bond. We can do hydrogen bonding with that. And so those are some solvents that would be polar protic. For polar aprotic, we still have those electronegative atoms because we still do need to have those polar covalent bonds in that solvent, but those electronegative atoms are not attached to an H, so they can't H bond. So here we have our oxygen attached to a sulfur. We have our nitrogen attached only to carbon. There's no H's attached to that nitrogen. There's no H's attached to this oxygen. And then same here, no H's attached to that oxygen or no H's attached to that nitrogen either. And so those are polar aprotic solvents. So things like DMSO, dimethyl sulfoxide is what that stands for the dimethyl sulfoxide. Acetonitrile, this is that nitrile functional group that we learned about, acetonitrile, because there's two carbons there. Acetone, we kind of saw that as a pi electrophile before, but now we're going to see this more as just a solvent in these reactions. And then dimethylformamide, this is that DMF, that's another example of a polar aprotic solvent. So how does this influence the reaction? Well, we'll take a look at these two reactions, A and B, done with the same electrophile. So we have the same leaving group, same carbon chains, the same primary electrophile. So nothing that we've talked about so far about the electrophiles has changed. Same exact nucleophile. So we have the negatively charged sulfur atom once we split up that sodium and sulfur bond, which we will do for our mechanism. The difference is the solvent itself. So we're going to draw the mechanism for each of these. So we're going to have our nucleophile attacking the alpha carbon, making the leaving group leave. That's going to happen for both of these identically. And we're going to end up with our product plus our leaving group will associate with the sodium. And that same product is expected for the second reaction as well. So nothing's really changing about those products or the nucleophiles or electrophiles. What is changing is the solvent. So what we have to think about is what we need to happen is the nucleophile and electrophile to come together to do this reaction. Anything that's going to stand in the way of this nucleophile reaching that electrophile is going to hinder that reaction. It's going to slow down that SN2 reaction. It's going to slow down that rate. If the nucleophile is having trouble getting to that electrophile, that's going to slow down the rate. And so where the solvent comes in is that the solvent can actually interact with the nucleophile, and it's actually by interacting with one of the important components that is part of the rate in that reaction, we are going to be slowing down that reaction. So the one that can interact with that nucleophile is actually the ethanol. So if we're thinking about that nucleophile, what it looks like, so we have our SCH3, we have our lone pairs around that, it's negatively charged, And what can start to happen is with the ethanol, because it can H bond, it's going to start H bonding with that sulfur's lone pair. So that sulfur is going to, the lone pair is going to be able to interact with the H from the ethanol. In this case, this would be any kind of polar protic solvent. It could interact with that. So we're going to have this starting to surround that nucleophile. So we're going to have that H, OET. We're going to have a variety of these types of interactions. And that, by interacting it with it, basically this nucleophile is going to be surrounded with kind of like the shell of that solvent. And so now when the electrophile is coming around it, it's going to have a hard time actually getting to that electrophile because all of these solvent molecules are going to be in its way. They're basically not leaving it alone. It's just H bonding with this solvent, and so, or H bonding with this nucleophile. And so what's going to happen is that nucleophile is going to have a hard time reaching the electrophile, which it's because it's interacting and it's kind of taking away from that nucleophilic component. It's getting in its way. It's affecting one of the components that is important for the rate of the reaction. And so that solvent is actually going to slow that reaction down. And so B is going to be the slower reaction. The faster one is going to be with acetone because we aren't able to H bond. So acetone had this structure here. We aren't able to H bond because there's no H's attached to that oxygen to actually H bond with the negatively charged sulfur. The oxygen with its lone pair is certainly not going to do that. So there's nothing to actually H bond with that nucleophile. And so that's not going to affect that nucleophile. The nucleophile is just going to go kind of easily through the solvent, find its electrophile, and do its reaction. And so A is going to be the faster reaction because it's in a polar aprotic solvent. And so it doesn't interact as well with the nucleophile. And when it would interact with the nucleophile, it would slow it down. So polar aprotic solvents, those are the types of solvents we want to choose for our SN2 reactions. Why did we even really bring up the polar protic solvents then? This is actually going to be useful as a solvent for a different type of substitution. So when we're going a little bit of a different pathway, we're doing an SN1 reaction that we're going to talk about in a few chapters. This SN1 reaction with this different mechanism is actually going to work better in our polar protic solvent. So for SN2, we're looking at just the aprotic. We don't want anything to get in the way of that nucleophile. We want it to be able to find that electrophile as fast as possible, do that reaction. That's going to be better for that SN2 reaction.